All right, so the last section you guys did was all about graphs, taking a graph and then finding its slope graph, right? What was the section before that? I know I still have the homework for it, so you can't go looking and figure that out. Okay, it was derivatives. How? What did we do to find derivatives? We had lots of steps. There's a four-step method. The four-step method has a name. It's called the limit process, right? The limit process for finding the derivative. And so what we're going to do is we're going to use the limit process for finding the derivative on these problems. So here are the directions. You're going to consider the following derivatives. Some of these you've already found. So I hope you have, or somebody in your group that you're working with has your notes from section 2.4. We'll save you lots of work, about half the work, because you already have some of these answers, okay? And it says next to it, done in class, if we've done it. So you don't have to go like, did we do this one or not? It says so, okay? Done in class. And then it says find the rest of them yourself now using the algebraic method. That means the same thing as limit process. So this phrase, I need a white pen, hang on. This phrase is the same thing as limit process. And then complete the basic rules as you discover the results of this exercise. So we'll do the first one together, just to make sure everybody's on the same page, and then you'll do the next four in groups. How's that sound? Okay, so the first one is in your notes from section 2.4. It says it on your paper. So grab out your section 2 or section 2.4 notes and look for what the derivative was when you had the function 6. $2.4. Was it 2? Oh, it's 2.5? Oh, I think this was an old edition of the book. That's why it's 2.5. I'm sorry, guys. 2.5. Let's fix it. Thank you for that. I'll get those notes fixed, too. 2.5. That's right, 2.5. Okay, 2.5. Somewhere in there we did the derivative of 6. What was the derivative of 6?
0.
It was 0. Okay? So one of those, which problem number, not all of them are numbered. I don't always number my problems. Letter F? Letter F, okay? Number F. We can call it number F, it's okay. All right, on number 2, that's not from your notes from 2.5. So we're going to do that one together. So the first step, I don't have as much space as you do, so I'll move up here. The first step is to find, what's the name of my function? K. K of x plus h. So K of x plus h is actually just 6, because there's no place to put the x plus h because there was no x, right? Step 2 was to take that function that we just found, k of x plus h, and subtract k of x. This is the one that you thought was really weird. It is really weird, because you get 0, right? Actually, let me put that over here for space purposes. Step 3 is to take that quantity, k of x plus h minus k of x, and divide by h. So now we have 0 divided by h, and we still end up with 0, right? And then the fourth step is to do the limit as h approaches 0 of 0, and we get 0. So the answer to this question, so if this is g prime of x is 0, k prime of x, we just found out, is also 0. Okay, so these are our 2 example problems. And it says, using the above 2 examples, what's the general rule you see here? When you have a function is equal to a constant, what does it appear that the derivative is going to be? 0. So you're filling in what it looks like the rule is telling you. Well, it looks like every time I have a constant, and I've only done 2 examples, so we could be wrong about that. But it looks like when I do this that I end up with a derivative of 0. Okay, do you understand the process of what we're doing? We're going to take 2 examples, and there's one place where there's going to be 3 examples, but most of them are 2 examples, and try to generalize the process of what you're seeing. Yes, Hannah?
Where did you get 6 for number 2?
We had it from our notes in section 2.5,
She just used K, but she meant G.
letter F.
Oh. What?
What's wrong?
Like, you were writing, because you're writing out the
Oh,
function of x.
that's your problem. I didn't have the right number here. How about I use the right number? I'm sorry. I was on the wrong line. How about
But
that?
then number 1 is from my notes.
Number 1 is supposed to be from your notes. That was the 6, which apparently I just redid. But negative 2 works the same way, right? Yeah, it does. Negative 2 minus a negative 2 is 0. Thank you for correcting me, Hannah. I appreciate it. Okay. So it looks like when I take the derivative of a constant, I get 0. That's what this is supposed to be showing me, yes? Okay. So I need you guys to put yourselves in pairs. And you guys are terrible about like moving your desks. So we're going to do it. I want to see everybody's move desks closer together, staring at each other, something, so you can work through these problems, okay? Your next set is to look at 7x and 5x. And one of them's from your notes, I think. Yes, 3 is. All right, so we're going to run through this pretty quickly because I've talked with most of you as I've been going around. I think everybody's on the right track. So what I'm going to fill in with you is what you're getting for the answers, and then we will make sure everybody has the right general rule written down. So what was the derivative? Hey guys, what was the derivative of 7x? It was 7. And what was the derivative of 5x? It was 5. So using those two examples, we conclude that the derivative then of kx would be k. So if we have kx, it's going to be k, and that should make sense, and here's why. Derivatives are actually what? What are we finding? Slopes. What's the slope of the equation 7x? It's 7, right? It's just the constant that's in there because a line has a constant slope. So this makes sense. What did you get for, or look at your notes from what you had before, what was the derivative of x squared? 2x. And what was the derivative of x cubed? 3x squared. So in general, when we have an exponent, x to the n, right? What is the derivative of x to the n? Nx to the n minus 1. And this is the only, probably the only thing from calculus that my husband remembers, is that rule. I don't know why that one is it, but this is the one people tend to remember. I don't know about it being the best, but maybe the longest, because it's been a long time. He remembers this rule. The last two are a little bit funnier, and those are the ones that some of you struggled, especially with number 4, with how to write it. What did you get for the derivative of 4x squared? 8x. And the derivative of 3x squared? 6x. And what I was trying to help you guys see is what was really going on is you were getting 4 times 2 of 2x and 3 times 2x. Did everybody realize that? So the 4 and the 3, the constants, didn't actually change what happened to the x squared. What happened was the constant k is still involved in the problem. And in general, what happens then is the derivative of f of x, which is f prime of x, gets multiplied by that constant. And I know it looks kind of funny there right now, like I'm writing it silly, because we know it was multiplied by this, bring down the exponent and so forth, but we don't always and we won't always have exponents. In particular, as soon as we switch into 3.2, we're going to do this with logs. It's not going to look the same, okay? But it's still going to be k times f prime. And then the last 3, 2 of which you had done, the first one you hadn't. What was c? I think the first one was the one you hadn't. What was the derivative of negative 6x squared plus 7? Negative 12x. What was the derivative? What was this? D prime of x. What was the derivative of x cubed minus 5x? 3x squared minus 5. And what was the derivative of negative 2x squared plus 3x? How about negative 4x plus 3? Is that what you got? Okay. So in general, what happens when we have two functions that are added together when we take their derivative? What's going on? We take their derivative separately, and then we add them together, right? So this is f prime of x plus g prime of x. And you might think, well, obviously that's what you would do. Why else would you do? Like it doesn't, what else could you do? Well, the catch is that this is really nice and works for addition and subtraction. It doesn't work for multiplication and division. and we'll explore that when we get to the multiplication and division section right after spring break, that this doesn't work for multiplication and division. You can't just combine them like this, but it does for addition and subtraction. All right, the one last piece of information for us to recall is how to rewrite things that look like denominators and things that look like radicals in exponential form. Because if you have the power rule, which you now do, right? In x to the n minus 1, you have the power rule. If you can turn something into a power, then you can use the power rule. So, but we got to be able to turn it into a power. Does anybody know how you turn 1 over x to the n into x to the power? Negative n. So if the exponent is in the denominator, right, the base and the exponent are in the denominator, you can bring them up to the numerator by making the exponent negative. We can do something similar with radicals. This doesn't work if there's like addition and subtraction under radicals or addition and subtraction in denominators. Only if the base to the exponent is the only thing there. Okay, so don't go carrying things too far. It's just a simple variable to an exponent. Does anybody remember how you rewrite the nth root of x to the m as an exponent? Yes, good job. So this would be x to the m divided by n. So like in particular, if you were writing the square root of x, this would be x to the 1/2 because there is an understood, whoops, I didn't mean that there, 1 here and 2 here. Okay? We see x to the 1/2 and things like that more frequently than this arbitrary m and n business.